So let's try to do some visualization for the Kkt condition. Pretty much the visualization here is for us to give an intuition about why the Kkt condition is indeed necessary for each local optimal solution. Okay, so let's say we have an example here. We want to try to maximize x1 minus x2 subject to one constraint, another constraint. So both constraints here are nonlinear. And we may see that the first one is inside a circle and the second one is the region outside the circle. So if you spend a few time to take a look at these constraints and draw some pictures, you're going to get a figure like this. The feasible regions is here, okay? And because we are trying to moving toward the right bottom corner, so we're going to move toward this direction, and your optimal point is this corner point. Even though the boundaries are not linear, but conceptually this is still a corner. So your optimal solution here is square root of 3 and negative 1. Let's call this point x start. So we now want to get some ideas about that gradient thing about our Lagrangian relaxation, right? So let's take a look at gradient f, gradient g1, and gradient g2 at x star to see whether we may find anything. So for gradient, we know how to deal with that. Gradient f is 1 minus 1, okay? I hope this is not too difficult for you. Differentiate f with respect to x1, differentiate f with respect to x2, okay? So it has nothing to do with your x, it's always 1 minus 1. You always want to move along this direction to improve your objective function, okay? That makes sense. And also your g1 is here, okay? g2 is here. Don't forget that we always write down our constraints as g as less than or equal to b, okay? So you don't care about the constants. Also, you also know that after your differentiation, the constant goes away. So you only look at those non-constant terms, that's your g1, or the non-constant terms, that's your g2. So you do first order derivatives of g1 with respect to x1, you are going to get 2x1, okay? I hope that makes sense for you. And then 2x2 if you differentiate with respect to x2. For g2, that's the same thing. So please verify this by yourself. And then we may also plug in x star, and x star into these three functions. So in general, you should consider gradients as functions. And you may plug in a specific point into this function to get a specific vector for the gradient at that point, okay? So once you do that, we may now do some depiction on the graph. So our gradient f is here, okay? So it is perpendicular to your isoprofit line. So this is 1 minus 1. This is your gradient f. Then let's take a look at our gradient g1 and gradient g2 at x star. So numerically, we may show that their values are 2 square root of 3 minus 2, and so on and so on and so on. If we depict them onto your graph, gradient g1 is here, gradient g2 is here. There are some observations we may have. For gradient g1 at x star, you may see that it is perpendicular to something. To what? It should perpendicular to that constraint, right? So for your constraint, you may do a tangent line here on your point x star. Then your gradient g1 is going to point toward the invisible part for your constraint, okay, in a perpendicular angle. So there are two things. First, why it should be perpendicular to your tangent point? That's simply because your gradient is the max speed increasing direction, okay? So it should perpendicular to that for your circle. That makes sense. And also, it's going to point toward your invisible part. Why is that? Because for your constraint here, for this one, you know, its visible part is inside its circle because it is smaller. So inside the circle is the smaller side. Outside the circle is the bigger side. Your gradient is increasing. It's the increasing direction. So in this case, necessarily, it must point toward your visible part. Okay, so invisible part. So I hope that makes sense to you. Okay, so that happens for G1 and also that happens for G2. For G2, you may see that it's also perpendicular to the tangent line. Okay, the tangent line is tangent to G2. Well, G2 is the circle here. Okay, so you first have the tangent line and then you have a perpendicular angle. That gives you gradient G2. Here you may see that your G2 is point toward your the inside of G2 instead of outside. Why is that? Because for G2, the inner part is the larger part. The outer part is the smaller part, okay, according to the functional form of G2. And your gradient is an increasing direction. So that's why it should go toward the invisible part, okay? So always don't forget to first organize all your constraints into this particular format. Your G should be put at the smaller side of your inequalities so that when you do these gradient things, you're going to get the required first order condition for your Lagrangian in this particular format. If you put G at the larger side, there will be some place that you need to multiply a -1, something like that. So that's going to create a lot of confusion. So don't forget to always reorganize your formulation before you really apply the Kkt condition. Okay, going back to here. So what do we have now? We may see from the graph that gradient G1 and gradient G2 form a place that covers your gradient f. So that means your gradient f is in between your gradient G1 and the gradient G2 at x star. Okay? The existence of your lambda non-negative. It means that you may combine gradient G1 and the gradient G2. You may combine these two vectors in a non-negative way to form your gradient f. Okay? If your gradient f is actually here, then you need to multiply gradient G2 with a minus, is a negative term, to make this happen. Okay? The fact that there exists a positive lambda, non-negative lambda, to make the equality hold means that your gradient f is in between your gradient G1 and the gradient G2 at this particular point. And what does that mean? Well, very clearly, that means we don't have a feasible improving direction. The gradient is an improving direction, is the fattest improving direction, okay? So along this direction, if this is okay to move along, then your current point is not feasible, okay? So it is because that this direction is in between these two gradients with respect to constraints, so that you know it is impossible to move along this direction. It's also impossible to move along this direction or this direction or this direction. But if you take a look at this carefully, it is possible to, it's also impossible to move along this direction. So for all these directions that I just draw, you just cannot move along that ways. So if that's the case, then there is really no way for you to improve this particular point. But for example, suppose the objective function is actually maximize x1. If that's the case, then your improving direction would be this direction. Okay, your gradient would be here. The gradient is not inside your two gradients with respect to G1 and G2. And what does that mean? That means the current solution is indeed not optimal, because while the current solution is just here, you still have other solutions that is actually better. Okay? So basically, the geometric idea of this particular equality is that if this is possible, then your gradient f is within all your gradients of constraints. And that means there is no way for you to keep improving in a feasible manner. So that's the idea of the gradient with respect, or the gradient of Lagrangian. So the last thing is the complementary slackness. Complementary slackness simply tells us that only those constraints binding at x star matters. So if you have a constraint that is non-binding at x star, then your lambda would be 0. If lambda is 0, then some term is going to be taken away, and you don't really care about the gradient of that constraint because it's not binding, so it's useless in some sense. Okay? So that's pretty much the idea, the geometric idea of the Kkt condition. So it's not a proof, but maybe it helps you to understand what this constraint wants to capture. It simply wants to forbidden, to disallow the existence of feasible improving direction. So that's the idea of the Kkt condition.